I know. All right, can we all see me? John, do you see me? Give it a moment. Let me know if you guys can see or hear me. You see it? All right, we see it? Awesome. All right. We might have some buffering issues. That's due to the internet here being very, very slow at the moment. So just bear with me, guys. All right. Okay. All right, so we're seeing my screen. Well, that's okay. We don't have to see my face. Okay. How bad's the lag over there, John? Does the audio sound okay?
I don't know yet.
That's okay. We'll see.
It's like 20 seconds behind.
20 seconds behind? All right, we can work with that.
How bad is the lag was just sent through?
All right, that's fine. Okay, well, there's going to be some lag this time around for you guys that are joining us. Let me go into the forum real quick.
Audio sounds like kind of weird. I have no clue what's causing it.
All right, that's fine. We can debug that.
It's not horrible. It's just strange.
Okay. Awesome. We can hear me. Everyone can see me. Perfect. All right. I guess we can get started then. Also, you're going to want a laptop. You can hop on one of those if you want. All right, well, you guys will be able to see me. You guys can't. Working with the video stuff right now. So next session will be a little better. There won't be this giant lag on your guys' end. But anyways, welcome to A Walk with fastai2. So this is basically a culmination of the past 3 sessions that I've done this sort of study group course here at the university. And it's like the practical deep learning for coders that Jeremy Howard, who originally made fastai, does. But instead, we're going to go subject by subject in more depth, show a bit more techniques, and also doesn't have as steep of a learning curve. So ideally, this should span maybe 1 to 1.5 hour lectures with about an hour to an hour and a half for you guys to work on some projects. Some days that'll be more, some days that'll be less, depending on how complex the topic is or how simple it is. And that's how this is going to be run. So a little bit about me. I've been doing fastai for about 1.5 years now or so. I picked it up right when Jeremy did the version 3 of the course. I've been working on it basically every day since then. I've done a few projects, most involve fastai. I did a language model project. I've done some image classification along with, honestly, building this course, because a lot of what you're going to see is very different from what the course offers. And so there's a lot of little projects that'll be tagged in along the way. And then I'm a university undergraduate still. I've got another 1.5 years until I graduate. And I have a software design and development major with a minor in environmental science. So why did I even make this? Jeremy has the course. Why on earth did I start this? So first, here at the University of West Florida, people aren't quite prone to deep learning and the machine learning aspects and the newer techniques as opposed to other universities, especially at the undergraduate level. And so I wanted to bring that to you guys. And yes, we're good? All right. And so from that, I sort of designed this study group to where we have this cool FastData library that allows us to use these state-of-the-art algorithms and techniques in a way that's not necessarily dumbed down, but able to be shoved into your guys' faces as undergraduates, and you won't sit there and freeze and scream and run for help. And as I said, this is going to have a lot of techniques that weren't necessarily brought up in the course. They might have been mentioned, they might not have. And so we're going to kind of explore all the aspects between NLP, tabular, and computer vision. So here's the course schedule. So I split it up into blocks where the first month and a half-ish, we're just going to work on computer vision. And then we'll work on tabular neural networks followed by natural language processing. So you'll notice that a few things correlate with the FastAI lectures. Like lesson 1 and lesson 2 are basically going to be how Jeremy did his course, because they're very good introductory lessons. However, from there, we're going to start to get into a little bit more creative techniques, processes, and introduce a few different libraries. Such as if you look at lesson 5, we're going to do style transfer along with the new notebook dev library and how you deploy these models. So you can feel free to go through this block schedule. If there's something that you believe could be added on there, feel free to make a suggestion in the forums. And we can either work it into the course or help you guys bring it into the library so you can present to us as well with your notebooks. And if you ever feel like you're falling behind, don't forget these lectures are recorded and will be posted immediately afterwards. So they're just going to be there at your leisure. So requirements, Google Colab is what we're going to run all of our deep learning out of. So in a moment, I'll show you guys how we kind of set that up. And then Paperspace, which will also be free now that we have Gradient, we will be using for natural language processing because that takes a lot more time. In terms of communication and how I'd like you guys to sort of talk and discuss as a community, so we have a dedicated mega thread on the forum. It is this Walk with fastai2 thread that I'm sure a lot of you joining us online have read. And pardon the slow internet. But we're going to use this to kind of discuss everything related to the forums or related to the course. And if that becomes too cluttered, then I'll go ahead and just make separate individual threads for vision, tabular, and NLP. Along with that, don't be afraid to ask any question. No question's too stupid. We've all started somewhere. Yes, I've done this for 1.5 years, but I mean, if you go back and look through my history, I asked a lot of stupid questions that were answered immediately, and it was kind of I should have known the library works like that. No, you don't. You don't know until you do. All right, enough. Can we just start, please? Yes. So we're going to use Google Collaboratory. One thing I'll also mention real quick, all the notebooks are running out of the Practical Deep Learning for Coders 2.0 GitHub repository. So if you guys want to get access to that, it is at the beginning post here on our mega thread. And everything that we're going to run through, you can run along with me. So Google Collaboratory allows for free GPUs, essentially. And it's a wonderful resource. If this will ever load, I will show you guys. Otherwise, we will pop into here temporarily. This is what your environment's going to look like. And upon first opening, let's do that. You should get a screen somewhat similar to this. Now, to go through and open our lecture group's notebooks, you're going to go to File, Open, GitHub, and if you look for my name, the first repository that should pop up is the Practical Deep Learning for Coders. And then you can go through and select which notebook you want. So we're going to be working out of the pets first and then the custom. So I can just click this open in a new tab. and the notebook will open up right there for you to use, and it'll look very similar to how the notebook we're running in right now looks. So I'm going to close out of that, and that way we can save a little on the broadband. I've also added directions on how to get through it. This needs to be updated. That should instead be Practical Deep Learning for Coders 2.0. When you're running it outside of the notebooks that I have, you will have to change the processor to a GPU. I've also included directions, but you're going to come over to this runtime, change runtime type, and select your hardware accelerator. Now, Colab recently changed so that way you can only have one GPU process running at a time. Before, we could get away and have multiple. Now we can't. So you can only really run one notebook per session.
Sorry.
Yeah.
What's the name we search for in the...
Mueller ZR. Mueller ZR. All right, now, what exactly is fastai? So it's a library built around neural networks, and the goal was to help make the state-of-the-art more accessible to people. And ideally how this would be done is using the most minimal code requirements possible. Give me one moment. So it looks like the words in the slides are blurred a little bit. Let's see if we can zoom in and maybe that'll help a little. It might be a little blurry this time around. That's just because of the video streaming quality, and I'm sorry about that. But all the notebooks and resources are available on the repository. So the goal is to make state-of-the-art more accessible using the most minimal complex code needed. And fastai supports 5 to 6 data types. So we have computer vision, tabular, text, collaborative filtering, and just recently with fastai2, we now have medical imagery as well as its own separate library for you to use. We will not be covering collaborative filtering or medical imagery unless there's a large request to, then we can take a look at it. So what are we going to try and do today? We're going to set up the fastai2 library in Collaboratory. We're going to make a classifier for dogs and cats, start to understand the DataBlock API, and also work with our own custom images. So we're going to basically mix the first 2 lessons of the original course together. So that's why this one might be a little bit longer and a little bit more challenging, but I'm going to try and help walk you guys through it. So the library is constantly being updated, and so there's 2 different ways that you can go about installing it. One is with the editable install, which involves pulling the GitHub repository. The other one is just using pip. So this little script right here will go ahead and install all the libraries you need. And if you need to run the cell, you're going to do a shift and an enter while you're inside of it, for those who are unfamiliar with these notebooks. And this will run and purposefully crash your session after it's finished installing. That is due to Pillow needing a reboot when you're installing the new version. Another little tidbit to note about, fastai2 and fastcore basically update in tandem. So if you're doing an editable install with fastcore and a pip install with fastai2, you will run until you run into issues. And so the failsafe is always go back to using one or the other. So after this script basically runs, we can start using the fastai2 library. And today we're going to use 3 different libraries inside of it. The basics, callback, and the vision. The vision library tells us that we're going to use a vision task. The callbacks are how we can get access to various fit functions to help fit our model to the data, and the basics helps with some basic common functionalities that we're going to wind up needing. So I will give you guys a few minutes to run that script, make sure everything's going okay, and I'm going to check around over here and see what's going on. So one of the questions on this end was, what exactly is a notebook? So think of a notebook as a contained environment where we can run scripts in a localized area. So everything that we're doing, we can convert over to a .py file and run it as a script, but this allows us to interact with it. So now that we're running all this, all right, sorry about that. So overall, how we're going to wind up building our model and training is first we're going to make what's called a DataBunch, and then a learner with a bit of equipment to help our model fit, and then we're just going to train our model. And that's the end of the story for 90% of your issues. Now, what goes into there is a lot, though, so we're going to take it slowly. First, let's look at the actual data that we're working with. So we're going to use a function called untar_data. And what this will do is fastai has a bunch of these data sets stored away into S3 buckets. And it allows us to pull them down. So the one we're going to work with is the pets data set. Now what untar_data will actually do is grab this tar file from their bucket, unzip it, and return to us a path. Now, a path is kind of like a string that just says where everything's located, but you can also, from it, use a bunch of different commands that you normally would do in, say, the command line, like you can do an ls to list all of the files in there. You can list all the directories. You can delete files, add files, and what have you, just from this one object. So if you go ahead and run this cell, it'll download all of our data we need for the for this cats and dogs problem, which boiled down to is we're going to identify 12 species of cats and 25 species of dogs. So we're going to try and classify 37 different animals. 5 years ago to 6 years ago, the best was about 59%, and this was with separate classifications for the image, the head, and the body. And so we're going to instead try to do this all at once, using just one singular image. Now, this little bit right here, this NP random seed, this comes from the NumPy library, and it allows us to have reproducibility. So any sort of randomized selections, choices will all stem from the same seed, basically, whenever we're working with this. So if we have this seed set, we can come back a few months later, run the same seed, and get the exact same data split if we were trying to split randomly. So let's look at how our data comes in. Remember how I said that we can do a .ls? Well, ls will return an array of all of our items. And so we can select in there and grab the first 2 to 3 items. We can see that we've got an images folder and we've got an annotations folder. We don't care about the annotations because this is back to the separate classifications from the head versus the body versus everything else. We just care about the original images. So now let's build a data bunch. What is a data bunch? Well, a data bunch is a bunch of data that's coordinated and pipelined for our model to go and read, because they don't read simple images. We can't just send it an image and be on our merry way. It won't work like that. We need to convert it into something mathematical that we can perform these sort of calculations that our models are winding up doing. These are known as tensors. And so half the battle with the API and getting your data all set up is how do you take what you have and turn it into this tensor object and work with it. So to build a DataBunch, we're going to need a few things. We're going to need the path that our images were stored down to. We're going to want our file names. We have a little helper function called getImageFiles that will go ahead and grab all of our images. And now I know we can't quite see it from here. I was hoping we could. But our file name format is essentially we have the root, fastai, Oxford, Tripoli images followed by the name of the animal and a number. And so we're going to try and use regular expressions to extract that class name from it. Because all of our data, since this is a classification problem, needs to have labels. This is fully supervised learning, and so everything we want needs to have an answer to it. So that is known as our Ys. And so we have a collection of X's, which is our images, and a collection of Ys, all our labels. When we're going through and training, we want to do what's also called data augmentation. And so that's modifying the images, be it removing some parts, stretching it, turning it, rotating it. And this is all to help our model have a stronger sense of generalization when it comes to images that come in by giving it a lot more scenarios than you normally could with just standard images. So we have what are called these batch transforms and these item transforms. I'll go into that in a moment, along with our batch size. So our batch size says every time that I want to train my model, I'm not going to send all 900,000 images at once. Because what will wind up happening is they will be broken up into these batches where we try and send batches of data into our model. Otherwise, we're going to run out of memory very, very quickly. And so depending on the image size and how much available GPU RAM you have, sometimes you can get away with 64, sometimes 32, and as you'll see occasionally throughout the course, sometimes even 1. Because otherwise you will just blast through the 16 gigabytes of RAM or 12, depending on what you're using. So lastly, we're going to create what's called an image data bunch. A bunch of image data that is labeled and split for us to use. So we're going to pass in that path the file names, our regular expression pattern, our batch transforms, our item transforms, along with our batch size. And this will go ahead and prepare all the data for us. Now, the other thing you'll see on this batch transform is something called normalize. If you're unfamiliar with statistics, anytime we do any sort of analysis on data, we need to normalize everything so it all is within the same field. So with images, how we do that is we normalize the individual pixel values. So they all follow the sort of U-shaped curve that it usually has. Or I guess that's a hill, would be a better way to put that. Now, I threw a lot at you, and for those who are familiar with fastai, you kind of understand where I'm going for some of this, but a lot of you don't. So let's take a step away from the notebook and go into what exactly is going on here, how do I build a framework, and what is all the things I just mentioned. So if we go to slideshow and from the beginning. So when we're working with our data, we're going to first want to collect some data. So this is from a development standpoint and your company that's hired, you want to hire to do some analysis. Your general pipeline will be first you're going to want to collect the data and then clean the data sometimes. Sometimes it's actually helpful to just run the model raw on unclean data and see what happens. Jeremy's found that sometimes it works, sometimes it doesn't. If it doesn't, then go clean. If it does, then go from there. All right, looks like it wound up, giving us that. Let's see what we can do here. Because it suddenly went to me. Let's see what happens if I deactivate you. One moment, guys. All right. We'll just roll in this. Does it still show me?
We'll figure out in 30 seconds.
Yep. Give us one moment to check something out. Just in case we'll run it like this. All right, so generally how the pipeline winds up being is you collect...
It doesn't change back.
Yeah. We're still good. All right, so when you're a company, you're going to first want to collect your data and then possibly clean it. And then from there, you're going to train your neural network. So you're going to send it to your team, which in our case will be us, to go and try and complete whatever task we're wanting to do. Is it classify dogs and cats? Is it try and find the person in the image? Or try to see if some piece of article sounds trustworthy. And then we're going to evaluate our model on some unseen data. A lot of times this can be called your validation set. So all those transform we talked about beforehand, those happen on your training set. Two separate things. So for instance, we'll normally split the data about 80% goes into your training set, 20% goes into your validation. And the validation is not touched, it's only graded, and the model doesn't change based on how it did on the validation, only how it did on the training set. Along with that, I'm going to post a link to one of Rachel Thompson's articles that goes into great detail over how you can build a good validation set to properly grade your model depending on the task. And then after we go through a cycle of checking to see if our model is good enough or not, if not, we go retrain it, maybe clean the data again, then we can go and deploy. So that's what your overall pipeline will look like, and we're going to focus on these two. Now on to the DataBlock API. So with this DataBlock, we essentially have three different options we can go from. We have the highest level API, which is the DataBunch, which you just saw, that image DataBunch one-line call that we just did. We have four different types: image DataBunch, segmentation, text, and tabular. Now, going into what each of those are, so an image DataBunch is something like image classification. So is it a dog, is it a cat? Segmentation is, think the autonomous cars, where they're putting a mask around a person. And let's see how good the internet is doing for me right now. Oh, it's not too bad. So let's see if I can pull up an image of segmentation for us. Well, that's loading. We have text DataBunch, so that's anything that has to do with text documents. For instance, GPT-2 and BERT that came out recently, that's what they're dealing with. And here's some examples of segmentation. So you can see that we're sort of drawing on the images pixel by pixel, trying to discern whether something is a car, a person, or what have you. So you can see that this person's in green, this person's in blue, along with the road is in this dark sort of goldish color. And then we have tabular DataBunch, so that's going to be all of your numerical data. I know a lot of you here at the university, that's probably what you're going to wind up working with if you're doing research, just because the professors here are very interested in that. Then we have the medium level API, which is the DataBlock. So it has a lot more flexibility and is built more like building blocks, hence why it's a block. So we're going to focus on as many of the blocks as we can, along with build our own for something that the library necessarily isn't built for right now. So we have image block, mask block. Those are our images and our segmentation that we mentioned a bit ago. Point block, that deals with key points, so finding the joints on a person or trying to find the center of a head. Bounding box block, or BB blocks block, say that 3 times fast, please, I dare you, is bounding boxes are kind of like drawing an outline around where a person is. And so instead of the segmentation where we had person A and person B are colored, we would instead have a box that would be encompassing the individuals. And then we have text block, which is, like I said last time, with the text DataBunch, it's just working with text data. And then tabular pandas. Tabular doesn't necessarily have a block because we have to go about it a little differently. We'll go into that more after the image section that we're dealing with. And that's the blocks that fastai currently has. There's also a medical imaging, but that isn't necessarily a block per se. And then lastly, we have these pipelines and data loaders. They are the absolute lowest level, and they have the highest flexibility out of the other three options. And so that's very bare bones, working with the inputs that are raw, the outputs that are raw, and how do you turn them all into these tensors that everything needs to be. So we're going to focus on the data block portion. The general way of how you set it up is you're going to define what your blocks are. So that's going to be your input and your output. So your X and your Y. Your getters, so that's going to be how you're going to get your X, how you're going to get your Y. How we want to split the data. Are we going to split it randomly? Do we have already a pre-made split setup where we know what our validation should be and we know what our training should be? We need to label our data so we know what the answers are. And lastly, we data bunch it together and apply those transforms that you saw us do with the PETS data set a moment ago. So here's an expanded list of those blocks that I mentioned earlier. You'll notice there's a few that I didn't mention before: category block, multi-category block, and transform block. So all of these blocks are built on top of a transform block. So when you want to try and integrate into the library and use custom data sets, this transform block is what you're going to want to look at in the source code. Category block is for our Ys. So that's going to be your label. We want it to be a category. And multi-category block is saying that I have multiple categories at once. So it's a dog that is a Shiba Inu. That counts as two categories. It's a multi-category problem. And then our getters, so we have a get X, a get Y. Depending on what you're using, a lot of times these will be determined and you don't have to adjust it. Mostly it's just the get Y, how you want to get your labels. A lot of different options, as I mentioned. Today we're going to focus on random splitter, which randomly will split our data to a given percent. Index, grandparent, and func splitter, along with column splitter, we're going to go into in the course. Mask splitter, not so much, I believe, but there's documentation that you can look at along with source code notebooks, if that's of interest to you. And then we need a way to label it. These are our labeling options. Parent label is just going by the folder that it was stored in. But today we're going to be using this regex labeler. And then lastly, the data bunch. So when we data bunch, we're going to need a few different things. We're going to need the path for that our data block was defined as to what the items we want to use. We're going to want a batch size, and we're going to want some transforms. So one key difference between those item and batch transforms that you saw is where they actually run. So the item transforms are running on each individual item as they come in. And you want these to resize your images so they're all the same size so we can fit it into our model. Because we can't fit an image that's, say, all right, my last one was 126 by 960. If my next one's 224 by 224, that won't work. For everything to work out together, they all have to be the same size. And so the item transforms is where you're going to want to do this. And that's going to be running on your CPU. Now the batch transforms run on the GPU. So you can do things like convert all the pixels into numbers. We can plop that on the GPU and make it run a lot more efficiently. Along with that normalization that we saw before, that's where we'd also put that. So now that we kind of know how everything's doing and working, let's go back to the DataBlock API. So we're going to rebuild this now using a data block, that medium level. So the first thing we want is our blocks. So we're going to get in an image, and we want to output a category label, a class, either Shiba Inu, Husky, what have you. So our blocks are going to be an image and a category. From here, we want something to grab our items before we use this get image files function. So we're going to use that here as well. Splitter, we're going to use another random splitter. And when you don't pass any parameters in, it's assumed that you're doing an 80-20 split. So 80% of your data goes into training, 20% goes into validation. And then lastly, we're going to want a get y. And so this is how we want to grab our answer, essentially. Grab our category. And so this regex pattern will do the job for you. And so now we can, now what this will actually create is an object that has this pipeline of, okay, let's go through, get our blocks, get our items, split it, and then put everything together in a data bunch at the end. So we're going to grab our images path because DataBunch is expecting some items. We're going to grab our item transforms, which was the resizing. If we go back, that was this random resized crop. So our stuff is all going to be shrunken down to a 460 by 460 image. And then we're going to pass in our batch transforms, which was our augmentation along with normalization, and a batch size. So we did the same thing that we did earlier, but this was to show you kind of how this middle-level API works, and that's one of the major differences between fastai version 1 and fastai version 2. The mid-level API was not very strong. It was clunky, and while it could work, it didn't make much sense in a way to where you could apply it to many different things. Here, instead, it's the same 4 to 5 different patterns over and over again. How are you going to get your inputs? How are you going to get, or what are your inputs? How are you going to get them? How do you want to split them? And how do you want to label them? That's going to be the same for every single problem now. And honestly, it's one of my favorite things about this library now. From here, we have this DataBunch object, which has, all of our information labeled, augmented, and what have you. So let's take a look at it and make sure that our regex labeler actually worked. So we can call what's called a show batch, and we can pass in the maximum number of images we want to take a look at, along with a figure size. And so here we can see our labels look okay, and our images don't look too augmented, but they do look somewhat augmented. This is due to how pipeline works now. So all of our stuff was already augmented, and we took a step back in order to show it. So that way it was something that was relatively viewable. And let's look at some other aspects that this DataBunch object has. So we can look at our vocabulary and see just, how many species did we have? What were their names? So the first bit here, so what you're looking at is actually an array. And it looks a bit different than an array because we have this weird parenthesis 37. This is an L object. And it's something that Jeremy and Sylvain sort of discovered and made while they were building this library. What an L is capable of is kind of a dictionary and an array with a few extra bits. So we can see here that we have 37 objects in here, or 37 different files, or 37 different items, there we go, along with what they actually are. And an L doesn't necessarily have an item type. So we can store whatever we want in here, and it won't throw us any errors. Whereas, other languages want only an integer array, only XYZ array. Not the case here. Now, what we can also look at is what's called the O to I. And in the original version of the library, this was called C to I. Class. So for those of you that are watching and are kind of scared about it right now, we're not going to look at it. We're just going to use CNN Learner, which does a lot of the steps for us. So a CNN Learner requires a data bunch, an architecture for us to use. This is our model. Whether or not we want it to be pre-trained, and a pre-trained model allows us to do what's called transfer learning. So a lot of these models trained for many epochs. And cycle through the data a long time in order to become decent in this baseline data set called ImageNet. What we can do, though, is instead of retraining a model for many epochs and having to worry about that, we can borrow their weights, borrow what their model did, and reapply it to our problem. And it can train our models faster as well as improve the accuracy compared to if we were just training on our data set. The last thing we need is a metric. So this is how we're going to reasonably understand how our model is doing, because all of these have loss functions that will output a various decimal number that won't make too much sense to us right now. But error rate, that makes a lot more sense. The last thing we're going to do here, and this will be new to you guys, fastai v1, is this 2FB16. If you're familiar with this, that's mixed precision. So that is, we're training on a mix of 32-bit and 16-bit. Originally, it didn't allow you to train vision models much faster. This time around, though, when I was playing around with CNN Learner, I did notice improvement. So basic story right now is mixed precision allows you to train your models much faster. Now here, you'll notice that we never actually declare our loss function, how we want to grade our model. That is assumed through our DataBunch. So CNN Learner can pick up that we want to do classification, and so it will use a loss function called cross-entropy loss. And as well as that, something called an optimizer is used whenever we're training these neural networks. And the optimizer is essentially, when we train, imagine we have this sort of bowl almost. And we start at the top of the bowl, and we want to traverse down to the middle. The middle has all of the exact weights that we want to get the best accuracy. And we're navigating down that bowl with a blindfold on. So we can't feel around for what we're disoriented, and it's in zero gravity. And so we need an optimizer that will help walk us through getting to that center. And the better the optimizer, the less steps it takes and the less tries it takes in order to get to the bottom of that bowl. Atom is one that is very, very powerful and strong and has been state-of-the-art for a little while. fastai it's been using it since I've been here and a little before that. So the past 2 to 3 years, this is what they've been using. So from here, let's go through and actually train our model. So how do we do that? We're going to use this fit1cycle function. Now, we're going to pass in the number of epochs we want, and an epoch is how many times we want to iterate through all of our data once. So here we're going to iterate through it 4 different times and learn as much as we can. And so if we notice, it'll take a few minutes for this to actually run, depending on what you're training. Language models are notoriously long. Tabular models should be very, very fast if done well. And then the image models are kind of in between depending on what you're doing. So here it takes about 1 minute and 12 seconds depending on what GPU Colab gave you. That could change, it could not change. And if you fit for 5 epochs, go ahead and try running that for a little bit. You should hopefully get somewhere to around 6%. So we'll take a quick little 5 minutes for you guys to go ahead and try running out the code. I can debug with you guys here, and we can then move on. All right, so one question I kind of got out here was what is exactly these models? And one way to think about them is, so we have the equation y equals mx plus b, right? And let me actually see if I can.
Or we could see if there's any AI using those Spotify.
Let me see if we can wind up. Anyways, sorry about that. So these models are basically y equals mx plus b. So we all know that mathematical formula, right? We all learned it in high school, hopefully before high school, in some cases. But it's set up to where y, so m, x, and b are all these matrices. And m is kind of a set amount to a certain extent. X is our input, and B is just some addition. And so what we're actually fitting is those two. We're fitting B and we're fitting M. Now, what it actually winds up being is a very, very complex M and B, because we have these models that if you actually run the ResNet34 call and just type ResNet34 and hit enter, you'll notice it's this humongous model. And so that's where the matrix calculus comes back into play. So you don't necessarily know the math that's going on here. That's okay. We're going to go over it a little bit in the next lecture. It's going to be a bit more intense, but we'll walk through it together. And that's what we're outputting from all of these. So we'll go ahead and pick it up from here. That probably gave you guys enough time to run the models. And let's go ahead and save this away in case we, say, run out of memory and need to restart our instance, or at the very least, save those weights away so we don't have to train again. So what do we do from here? Well, we want to look at our results and see kind of how we did. And it's sort of blocked out for me there. That's okay. Let's see if it'll work here. But what we can do with our models. Hello. Okay, are we all still here?
Did everything explode?
I think everything just exploded.
AI is too smart.
All right, we're just gonna go from there and assume that it's running. So it's not necessarily loading right now, and it's not loading here for some odd reason. But from here, we essentially have a fully trained model, okay, that is able to get up to 6% error. Now, let's recall that in the beginning, I said that these models had, the state of the art was, what did I say, 59%? Using two separate inputs of where the head and the body was, along with the actual image. And we blew that thing out of the water. And that's just last 5-10 years. So a lot has changed in machine learning and continues to change. So from here, how do we figure out what our model's doing and how it's doing? We use something called a, well, let's just go ahead and see if this will work. Sorry about that. Next session should be a lot smoother. This is just, the first time in trying to figure out all the bugs. But we can use what's called a classification interpretation. And we can pass in our learner object that we made earlier. This allows us to go through and look at the classes that we missed and how we wound up doing. And if it would actually like me, I'll show you guys. But doesn't look like the internet's going to like me. So with this object, we can grab a few different things. So we can grab our top losses, which will grab us what exactly were the highest missed classes that we looked at, along with our confusion matrix. Now, it doesn't show it here, but in a moment we're going to start talking about our own custom data sets, and I'm going to give you guys time to work through your own. And that one I know does have a visualization. So now we're going to move over to O1 custom. And this is going to be custom image classifier models. One thing that you can do with Google Colaboratory is it is a Google product. And so we can use our Google Drive to store all this data, because otherwise it's running on a static instance. And so anything that's wiped after 12 hours, you're never going to get again. So first, make sure that you're saving your data at the very least somewhere external outside Google Colab, either your Google Drive or you download to your local drive yourself. Now, if you do want to use Google Colab, everywhere that we have a path that points to birds, so in my example, we're going to use birds. Everywhere that says birds, replace with drive, my drive, and this will point to the home directory in your Google Drive. Now, we're going to follow a tutorial that is basically how last year's version of getting image data from Google searches. And the first thing we want to do is reinstall our libraries. So it's not natively on Google Colaboratory due to the fact of how it's in development. So you're going to be running this 4-line cell quite a bit anytime you want to use a new notebook and use the fastai2 library. I have that bookmarked in the fastai2 start here thread that Jeremy made. And I'm constantly updating that with any issues that Colaboratory may have that you might run into. So if something installs incorrectly and it's broken, check there first and see. So after that, we're going to use the same libraries that we had before, so the basics, the vision, and the callback. And let's go through and grab some images. So the way how we're going to wind up having this work is first you're just going to Google search for anything. So let's go back to this segmentation image example that I had here. What we can do is, now I will say first, you're going to want to do this in Firefox specifically. Google Chrome and Internet Explorer, this will not work. So that's one of the issues that a lot of people ran into. If you don't have Firefox, quickly download it if you're wanting to do this. Otherwise, there's numerous Kaggle examples of data sets that you can classify. So we're going to assume that I'm in Firefox, even though I'm not really. We're going to pretend I am. And we're going to go through and turn up this console here. We're going to copy this this command cell and paste it into our console and run it. Now, if you're in Google Chrome, it's Control-Shift-J in order to get this console working. That's what's different between Firefox and Chrome. And
Both of its F12s as well.
John, how's the stream looking? All right. So what this should have done is, if you look at what the text document you just downloaded is as, it just says download. You can rename it to whatever you want. I recommend your class.txt. So in this case, we'll just call this mask. And go back up. We'll call this one mask.txt. Now, if we go through and open it, we have all of these file names and all of these image names. All right, we have a data set now. Let's go through and get those. So you're going to want to do this for every single one of the classes that you're going to want to classify. You could do wolves versus dogs, whatever you wind up doing. If you see that you get good results, go ahead, post about it on the forums. We have a show your work section section that you can go and say, hey, I did this, I did that. I absolutely invite you guys to do that, especially if you come up with some neat ideas for a data set. So in our example, we're going to use bluebirds, red-winged blackbirds, and blue jays. Those are just 3 birds that I grew up with in Colorado, and so it makes sense to me. At the time, I had 3 text documents, a URL's blue, URL's red-winged blackbird, and a URL's jay. So we're going to create some folders that have our class names, because we want to do that parent label where everything is set up into separate folders. It's easy for us to do because if we're having to do this manually, it's just a separate folder for every single class. And along with our text documents. Now, the next problem you're probably going is, well, how on earth do I upload these? So if we look on the left of the screen here, you'll notice this little open on the left pane tab here. If we go to Files, once it eventually connects, over here on the left, you're going to see a little upload button, and you can go through and upload your text document. And if you have issues with that, I'll go through and re-record this later showing what that looks like. Now that we have all of that, we have most of the prep work done. So you're going to want to upload all 3 or 4 or 7 of your text documents there. We're going to want to declare our classes. And here, if you really wanted to, you could just keep them as folders. And we're going to try and build directories from there, because we don't actually have anything downloaded yet. So we're going to use the pathlib library that we used earlier, whenever it was basically a string that had access to all of these sort of directory commands and controls. And we can use it to make a directory of a path that doesn't exist yet. So I created this path called birds, doesn't exist, and I called make directory on it. Now, parent equals true means make sure that if there's something above it, that's okay. So we're working in a base directory that's tied in between all these different subsystems. And exist okay says that if the folder does exist, then that's all right, don't worry about it. That way you're not accidentally creating multiple folders. Now you can see here it finally decided to connect. If I wanted to upload, I would go ahead and hit this upload button and pick one. Now we can actually download our images. So if you're unfamiliar with Python's coding, normally we have just a for loop, right? Where it's, from 0 to I and all you have is I. We're going to use a special function called enumerate. Now enumerate will actually keep track of 2 things, I and whatever you're using. So in our case, we're going to enumerate through classes. And so what's going to happen here is I is going to grab the index, so 0, 1, and 2. And N is going to grab the class names. So that's going to be our bluebird, red-winged blackbird, and blue jay. That's very helpful in situations like this, because now I can create a path F, or a path folder. That is my files. That is my classes. Or in our case, if you go back up, files, sorry, my bad. So what we can do here is path F actually goes to our text document. So that is the TXT we uploaded. And we're going to use this path in a helper function to download our images called download images. Now what download images is going to want is where we can find the folder we want to store everything into. And it probably doesn't exist yet, and that's okay. It shouldn't. The text document with all of our file names, or with all of our URLs, along with the maximum number of pictures we want to download. And so with this, you can pretty much download most any data set. Me personally, I worked with the iNaturalist dataset and actually subsystem in order to classify snakes. And so I was able to use somewhat a similar technique to download all the URLs and not have to store them necessarily locally. Now, we're going to go through and grab that for all of our URLs. And now we're going to make sure that we can actually open them. Because a lot of times you'll go through Google and you'll notice that some of the images just don't work. In our case, sometimes they don't have 3 channels, RGB, and we don't want to use them because we want all 3 colors. Or they're just unopenable, they're corrupt. And so verify images will go do that. Now, something a little different between the fastai1 and the fastai2 API. Verify images will no longer delete the files. What it will do is check to see if the file exists or not, and it will true if so, if not false, and return the file name. So that's why here you notice that I go through and grab, well, first we have our images stored in that L array I mentioned before. I want you guys to get familiar with the L. It's not scary, even though it looks kind of weird. Especially because I'm doing a plus equal here. That's appending. So the L is a very creative array function. And so hopefully this will help get you guys used to it, because it's very helpful. So we're going to go through and verify the images for all of the files in our path from our folder. So that's what this function is doing. Now, what we're doing is adding onto images any file names that were corrupt. So after running this, we can see that in my case, one of my Bluebird images was bad. Now, we don't have to go through and manually delete it or even do, say, os.remove. The path library allows us to just do something called unlink, and it will just get rid of it. And so we can go through and do it and say, for all my images, unlink it. And now we have a clean data set that we can, at the very least, open. And if we want to double check that, run it again and see that images returns an array of 0. Now from here, let's make a data again. This is basically going to be the same code as before, with the main differences being I am passing 0.2 into random splitter. Don't forget that if you don't pass anything in, it's still doing exactly that. And our getY this time is parent label. And parent label operates under the assumption that all of our labels are in the folder above where our file was located. So now we can take this bird's data block, DataBunch it with our path, some item transforms, some batch transforms, and this will assume that our, well, actually, there we go, the batch size of 32. If you don't pass in a batch size of 32, it'll assume it's 64. So keep that in mind if you forget about that and suddenly you run out of memory. That could be part of the reason. Let's look at a few of the images. So the data set here honestly looks a bit odd because all we have is a lot of feathers and not too much else to go on. Now I should also mention this was randomly selected. I did not select any of the images beforehand, and neither did you. We just put whatever the first, to some regard it will help your problem. And so here what we're actually doing is taking the last layer, instead of saying my output is 1,000, my output's 34. And so it's that last little layer that we're really training before. So now that we have that, we can unfreeze our model and say, okay, I trained that first layer as best I can. Let's let the rest of the layers play catch up and see if maybe that will help improve my model a little bit. So now we can do what's called a learning rate finder. So remember how I said we had these optimizers? These optimizers work with what's called a learning rate, and that is how fast we feed the images through our model and how fast we decide that it's going to make a decision. And if we have too fast a learning rate, then we're never going to learn anything, and you'll notice your loss function will just absolutely skyrocket. Whereas if we have too slow of a learning rate, eventually we'll get there, but on a much slower time span. This is all about getting to that center of that U that I mentioned. So if we have it too fast, we might overshoot. If we have it too slow, we won't overshoot, but it could take us 1,000 of those epochs to get there. We want to do it in as fast and efficiently as possible. And so we have this tool called the Learning Rate Finder, where we can calculate where the best learning rate to use is. And so here we have this weird outputted graph that looks like an N right now. Well, what does this mean? Let's take a look. The left is our losses, and the bottom is our learning rate. So we can try and discern, what we're looking for is when our losses begin to increase exponentially. From there, we know that learning rate was far too fast because now we're no longer learning. Our error rate is actually increasing. And so we want to find either somewhere in the middle of this drop or as close to the lowest point as we can will be the fastest you can possibly go. And discerning this learning rate will help us fit our model better. So now we can go to fit one cycle, and we can pass in a learning rate maximum. And so what this will allow us to do is train our model at a specific learning rate. If we pass in 2 learning rates, then that is whenever we have those. Remember how we had a frozen model and we had 2 basically layer groups, you could call them, where we had the frozen bit and we had the unfrozen bit. Well, we can pass one learning rate into the frozen bit and another learning rate into the unfrozen bit. And even unfreezing them, those layer groups still exist. So let's train the one that's already been trained at a slower rate, actually at a faster rate, sorry, because we don't necessarily care about them. Because when you think about what they're actually looking at, it looks like a whole bunch of junk. If you go through and look at Jeremy's lesson in the original course, you can see what that actually looks like, but nothing is discernible in those first 50 layers or so. Only towards the end do we start to see, okay, that's the face of a cat that I can see in the image that this model is looking at. And so that's what we care about. So let's train that last layer at something a little bit slower. If we pass in no learning rate, no second learning rate there, and we have frozen layers, it will assume that we mean about 10 times faster for the second layer group. So now let's train for only 2 epochs, just to see how it does. And the nice thing with fit one cycle is it allows us to train faster. So normally if you're looking at any PyTorch code, you will see just a fit function in which you'll see that they run for hundreds upon hundreds of epochs. We can do the same in 20. That's what fit one cycle allows us to do. Later, when we're a bit more comfortable, I'll show you guys exactly what fit one cycle is doing. But for right now, just know it's a technique that allows us to train our models a lot faster. So now we can save our model, and we're at pretty much the end of this diagram that I showed us before, where we were training our model and going through and evaluating. This evaluate on unseen data, in a sense, is our validation data set. Ideally, you would also want what's known as a test set along with it, where it's truly unseen data that is directly from whatever you're going to be applying it to. So if we're dealing with time series data, this would be, I trained from January 1st to January 31st, and now I want to see how my model generalizes on February's data. It's never going to be trained on it and only evaluated once to see how it does. If it doesn't work as well as I want, I'm going to retrain everything and then evaluate it again. And Rachel also, again, goes into this in her blog post. So now that we have this, let's go look at that interpretation thing that I mentioned before. So I said that we can plot a confusion matrix. So this is what a confusion matrix looks like. And this might be blurry for some of you on the recording. Sorry about that. But we can see here that we have the actual versus the predicted. And so we have bluebird, blue jay, red-winged blackbird, and bluebird, blue jay, red-winged blackbird. Corner to corner is it got it correct because we have bluebird, bluebird, blue jay, red-winged blackbird, red-winged blackbird. And everywhere else is exactly where our model was being confused. And so here we can see we got red-winged blackbird mixed in with a bluebird a lot, along with a blue jay versus a bluebird, which to a certain extent, that makes sense. If you go under the assumption that your model, you want it to be 100% right before you go into deployment, you're kind of doing deep learning wrong. It'd be great if we could get 100% accuracy on all of our problems, or even above 90%. A lot of times you won't see that. A lot of times it will be what is good enough given the background knowledge that I or my team has on this particular issue. And so in some cases, state of the art could be no more than 40%. All right, now you go to 46. Your model's doing pretty good. From our standpoint, that's 46%. My model's, a load of poop. Maybe not. So keep that in mind whenever you're training these models, and you might not be happy with how those results are. Consider first how everyone else is doing, and second, how complex is your problem. When I was trying to build my snake classifier, I never really made it above 75%-ish. And the reason for that is, okay, go look up an image of a king snake versus a garter snake. Those are very similar snakes, and the only way to tell is by a little spot on their head. The model's going to have a hard time trying to figure that out because it's looking at the entire thing instead of just the head. Now, the other thing we can do is plot our top losses. So these are the images that we lost the most. And how this is formatted is what the prediction was, what the actual answer was, the loss, and the probability that it was going to be that image. So remember, our loss function was, if we look here, we have our train loss and our validation loss. And then this probability deals with the fact of how these image classification models have what's known as an arg. So anything that we pop in is going to have a probability of being XYZ category from 0 to 1. And it doesn't, it's not the raw values, they're rounded to a relative percentage. And so off the bat, these models, you can't say, tell me I don't know that this, tell me that this thing isn't a red-winged blackbird or a bluebird. I'm going to show a lesson on how you can do that, but right now you can't. So don't freak out if you want to deal with that sort of model. I believe that is lesson 4 or 5. If you want, it's lesson 4 if you want to go look at how those notebooks look and what we're doing a little differently. And if that confuses you for right now, don't worry, we're going to go over it. So that's pretty much it for the lesson from me. I'm still going to keep the stream going, and we're going to do some, we can do some Q&A. I can help you guys with any questions, big questions that you're confused about. You guys here, do you have any questions? Really? All right. And how about on the stream? I hear we have a study group in Brazil right now. Awesome. Glad to hear that. So that's about it. I'm going to keep the stream up and running. You guys can communicate back and forth there or on the forums. It's going to run for another hour and a half. I'll stick around and I can help answer you guys' questions and debug you guys through problems. Thank you for coming.